We start a new module, impedance matching, and in this particular module we are going to cover the following contents. We will first discuss about L section impedance matching, then we will discuss the single and double stub matching. L section impedance matching will involve lumped elements, whereas stub matching will involve sections of transmission lines. Then we will see a very interesting matching circuit which is called a quarter wave transformer. We will discuss the theory of small reflections, and then utilizing the theory of small reflections we will discuss how multi-section matching transformers can be designed, and then we will consider another form of matching network which is a tapered line. This type of tapered lines can be easily designed using planar transmission lines. So, we start our discussion on matching network first, in general discussion on matching network. So, what is a matching network? An impedance matching network is a circuit which is placed between a load impedance and a transmission line. Now, this is the block diagram of a matching network. We have a transmission line, Z0 is the characteristic impedance and ZL is the load impedance. We know that if we connect ZL directly to this transmission line, then when ZL is not equal to Z0, there will be reflected signal and the power will not be fully absorbed by the load, it will be reflected back. So, what we do? We introduce a matching network in between. Now, this matching network ideally it should be lossless, so that the matching network itself should not dissipate power. So, in order to avoid any loss of power within the matching network, ideally it should be lossless. So, a matching network is designed in such a way that the impedance seen looking into the matching network is Z0. So, if you look at this point, then the load impedance transformed by the matching network will give an input impedance of Z0 here. A matching network can be found as long as ZL has a positive real part, and there are several factors which are taken into consideration when we design the matching network, and these factors are complexity, the matching network should be very simple, bandwidth, it should offer sufficient bandwidth, the matching should remain valid over a wide band of frequencies, implementation has to be also taken into consideration, it should be easily implementable, and adjustability, because in certain cases, particularly when the load is variable, the matching network should provide some adjustability with the variable load. So, these are broadly the factors which are taken into consideration when we go for the design of the matching network. Now, let us come to L section impedance matching network. It essentially uses two reactive elements to match an arbitrary load to a transmission line. So, the first matching network using L section, we are showing it. So, we have a series element J x and a shunt element shown as J b. So, depending upon the lumped element used, this can be an inductive element, it can be a capacitive element. Similarly, here also we can use an inductive or a capacitive element. Now, this form of matching network is normally used when the real part of ZL is greater than Z naught, or in other words, if we consider the normalized impedance ZL by Z naught, it lies inside the 1 plus Jx circle in the Smith chart. So, in the Smith chart, if you consider the circle r equal to 1, so inside the circle we will have r greater than 1, and which actually indicates the real part of the load impedance is greater than the characteristic impedance Z naught. So, this type of matching network or this configuration of matching network is suitable for handling the loads for which the real part of the load impedance is greater than Z naught. This is another form of impedance matching network using L sections. Here also we have a series and a shunt element, but you can see that the shunt element JB is connected first and then it is followed by the series element JX in series with ZL. In the earlier network, JB is in parallel with ZL. Here JB is in parallel with the series combination of JX and ZL, and this type of matching network is suitable when the normalized impedance ZL is outside the 1 plus Jx circle in the Smith chart. What does it mean is that real part of ZL is less than Z naught. Here also this Jx can be a inductor or a capacitor, this JB may be an inductor or a capacitor. So, you can see that for these two circuit configurations, essentially we can have 8 different circuit combinations using the lumped elements inductors and capacitors. For example, this may be an inductor, capacitor, like that. 8 combinations are possible. Let us consider the L section matching network that is used for the case when RL, the real part of the impedance, is greater than Z naught. Now, for this circuit, in order to have the impedance matching, we must have the input impedance looking at this point must be equal to Z naught. So, we will have Z naught is equal to Jx plus the parallel combination of JB and ZL, and 1 by ZL can be added to JB, and then the reciprocal of this entire term can be added to Jx, and that has to be equal to Z naught. So, if we multiply JB by R plus JXL and also take, if we multiply JB by RL plus JXL and also take RL plus JXL to the numerator, we get this expression, and then we can multiply this denominator term with Jx and Z naught, and then we get this expression. And from this expression, what we can do? We can equate the real and imaginary part. So, if we equate the real and imaginary part, so you can see that we will have, first let us equate the real part. So, we will have minus z naught b x l plus z naught. This will give another real term. So, minus x b r l, and then these two terms will be imaginary r l. So, minus x b r l plus r l, and rearranging the terms we can write b x r l minus z naught x l is equal to r l minus z naught. So, this is the equation we get after equating the real part only. Now, let us consider the equation that we get by comparing the imaginary parts. I have rewritten the main equation here. So, if you collect the imaginary parts from both sides and equate them, then we get z naught b r l is equal to minus x b x l plus x plus x l, and once again if we rearrange the terms we get x 1 minus b x l is equal to z naught b r l minus x l. And therefore, now we have a set of two equations, one from the real equating the real parts and another by equating the imaginary parts. And from this set of two equations, we can now solve for b and x, which are the unknown. So, we can solve for b and x. So, from this equation we can write x in terms of b, x l, z naught and r l. So, x can be written as z naught b r l minus x l divided by 1 minus b x l. Now, what we can do? We can substitute this x in the other equation. So, we substitute this x in the equation b x r l minus z naught x l is equal to r l minus z naught. So, once we make this substitution, and then expand, we will get this equation. Now, in this equation we can reorganize the terms. For example, this b square z naught term can be taken out from this term and here. Similarly, b z naught x l is here, and from this side we will get another b z naught x l, and finally we will be left with this quadratic equation in b, which can be solved, and we can write the solution of b as 2 z naught x l plus minus 2 z naught x l whole square plus 4 z naught r l square plus x square into r l minus z naught. So, and the entire term divided by 2 Z naught R L square plus X L square. So, this can be further simplified. We can divide both numerator and denominator by 2 Z naught, and then B can be written in this form. And from here we can simplify further. B becomes X L plus minus root R L by Z naught into root R L square plus X L square minus R L Z naught divided by R L square plus X L square. Now, we are considering the circuit, the matching circuit, for which R L is greater than Z. So, when R L is greater than Z naught, this term is always positive, because this term R L Z naught will be less than R L square. And therefore, what we can do, we can get from here, we find that we can always get a real solution for B. And once we calculate B, then we can calculate X from the relationship that we have written earlier. So, here B is already calculated, other parameters are known. So, X L can, here B is already calculated, other parameters are known, and therefore, X can be calculated from this expression. So, how we utilize this solution? Let us explain this by taking an example. So, we consider an example of L section matching network design, and let an impedance of ZL is equal to 100 minus J 50 ohm is to be matched to a 50 ohm line using an L section matching network at an operating frequency of 500 megahertz. So, let us design the matching network. We already have the expressions for B and X. So, if we substitute the values in the expressions for B, we get B is equal to minus 50 plus 100 by 50, 100 square plus 50 square minus 100 into 50, everything under root, divided by 100 square plus 50 square. Now, if this is computed, we will actually get two values, and these two values are 0.0058 ohm inverse and minus 0.138 ohm inverse. So, we have therefore two values of B. Similarly, if we use these values of B in calculating X, we will get two values of X, 61.2372 ohm and minus 61.2372 ohms. So, what we can have now, from these values of x and b, we can calculate the values for the lumped elements, the inductors and capacitor. So, let us consider the first solution. In this solution, we have omega c is equal to b, and therefore, c is b by 2 pi f. F is given to be 500 megahertz. B value we have already calculated. So, we take the first value of b, positive value of b, and then we get a value of c to be 1.85 picofarad. Similarly, omega L is equal to x, and therefore, we know the value of x. Let us take the first value of x that we have calculated and then divide by 2 pi f, f is 500 megahertz, then we get 19.49 nanohenry. So, this L and C combination actually will give a matching circuit which is shown. So, you have L, C and load impedance ZL and the transmission line Z0. We can have a second solution, because we had two values of B and two values of X. So, the second solution we find C is equal to minus 1 by 2 pi f x, and again substituting the value of second value of x, we get C is equal to 5.2 picofarad, and similarly L is equal to 1 by 2 pi f b. So, if we substitute the second value of b, we get a solution of 23.1 nanohenry, and this is the second network, and here you can see the series reactance. It is an inductance. Here the series element is a capacitance. Here the shunt element was a capacitor. Now it becomes shunt element becomes an inductor, and both the circuit will be able to match the given load impedance at the given frequency. That means, the load impedance of 100 minus j 50 at the operating frequency of 500 megahertz with these values of L and C used in the two circuits respectively. Now, we move to the second configuration of the L section matching network. Here you can see the shunt element JB is connected first, and then the load impedance ZL is in series with the reactance JX. Now, for this configuration, we use this configuration when the normalized load impedance ZL is outside the 1 plus Jx circle on the Smith chart. What does it mean? That when the real part of ZL is less than Z0. So, this matching network shown here we will use when RL is less than Z0. As before, we need to find out the impedance looking at this point, impedance or admittance looking at this point and equate. It is easier to work with admittance here. So, 1 by Z0 becomes equal to JB plus 1 by Jx plus RL plus JXL, and therefore, we can write 1 by Z naught is equal to J B plus 1 by R L plus J x plus X L. Now, from this equation, once again we separate the real and imaginary parts, and then we get a set of two equations from which x and b are solved. When this type of steps are carried out and x and b are solved, we get the expression for x to be equal to plus minus R L plus minus square root R L Z naught minus R L minus X L, and B is equal to plus minus square root Z naught minus R L divided by R L and the entire term divided by Z naught. Because of this plus minus signs here, once again we will get two solutions for x and two solutions for b, and we can map these values of x and b to a capacitive element and an inductive element, and therefore, we will get two circuits with b and x being represented by lumped elements, either a capacitance or a inductance. So, we have seen how we can calculate the values for the components of the L section matching network analytically. Let us now consider an L section matching network design using Smith chart. We consider an example how the values for the elements of an L section matching network can be found out using a Smith chart. Let us discuss the matching of a 100 ohm load with a transmission line of characteristic impedance 50 ohm at an operating frequency of 100 megahertz, and we use Smith chart to do this matching. So, when we consider matching in Smith chart, our starting point is the normalized impedance ZL, and which in this case is 2 plus J0, and after matching we reach the point Z is equal to 1 plus J0. So, in our case, since RL is greater than Z naught, we use the following circuit, where we have this shunt element JB connected to ZL first, and then the series element JX connected, and this L section network will match this load ZL with Z naught. So, for a Smith chart solution, what we do? We first plot this normalized impedance Z is equal to 2 on the Smith chart, and this is shown here. Next, we draw the constant VSWR circle, and then since we need to add an admittance first, we find out y is equal to 0.5 corresponding to this impedance Z is equal to 2. Next, we draw a rotated r is equal to 1 circle and we add J b equal to 0.5 to reach this point in the rotated r equal to 1 circle. So, at this point we can calculate the capacitor value that will be needed. So, our B is small b is 0.5. So, we multiply it by 1 by 50 the value of y naught to get B, and that should be equal to 2 pi f c, and from this we find the value of the capacitor to be 16 picofarad. So, at this stage we have found out this shunt capacitor that required to be connected across this 100 ohm load, and that will give us the real part of the input admittance to be equal to 1. Now, we need to add the series element. So, what we do? We come back to r equal to 1 circle, that means this circle. So, in order to do that, we draw this line through the center of the Smith chart and find the intersection point with r equal to 1 circle. Now, we read the value of the normalized impedance here. At this point, we have the value of the normalized impedance to be 1 minus j 1. That means, in order to reach to the center of the Smith chart, we need to add a reactance of plus j, and once we do that, we reach the center of the Smith chart. Now, this x is the normalized value which is having 1. So, 50 into 1 we equate with 2 pi f is 10 to the power 8 L, and then solve for L, and we get the value of L to be equal to 80 nanohenry. And therefore, we have found out both the elements of the L section matching network. The capacitor value is 16 picofarad and the inductor value is 80 nanohenry. And these values can also be verified using the analytical formulation which was described previously. So, we start our discussion on another matching technique which is called stub matching. A stub is a short section of transmission line which is either short circuited or open circuited at one end. Now, a single stub matching circuit consists of a series or shunt stub as shown in the figures. So, this is the figure for a series stub matching circuit. So, we have the impedance ZL, which is to be matched to this transmission line of characteristic impedance Z naught. So, what we do? We try to find out a length of the transmission line D such that the input impedance looking here, it becomes Z naught plus Jx. Now, this extra element Jx is nullified by connecting this series stub of length L, which can be open or short. So, this is one way of designing a matching network, and this type of matching network is called a series stub matching. In another design, we can find out the input admittance in such a way that y n becomes equal to y naught plus j b, and then add a shunt stub open or short circuit to cancel out this remaining j b, and therefore, match this to the line of characteristic impedance Z naught. So, if we look at both the circuits, what we observe that the design parameters in this type of circuits are the distance of the stub D from the load and length of the stub L, which may be either open or short. So, various design options are available. Now, let us consider an analytical solution to this series stub matching problem. That means, what we want to do? We want to find out this distance D and also the length of the stub L. As we have already mentioned that at the stub location D, the input impedance Z in is Z naught plus Jx, and we need to choose the length L of the stub, a short circuited stub or a open circuited stub, in such a way that the input impedance of the stub looking at this point has to be equal to minus Jx, and this will result into matching. Now, we know that the input impedance Z in can be written as Z naught ZL plus J Z naught tan beta D divided by Z naught plus J ZL tan beta D. And what we do? We equate the real part of Z in to Z naught, then we can find a solution for D. And once we have calculated D, what we can do? We calculate the value of x by substituting D, and then we find out the length of the stub so as to provide minus Jx. Now, let us try to see how we can derive the closed form expression for D and L. So, we have ZL is equal to RL plus JXL. We can write YL which is 1 by ZL to be equal to GL plus JBL. Now, let us define T equal to 10 beta D. So, therefore, we can now write Y in, which is 1 by Z in, to be equal to Y naught Y L plus J Y naught 10 beta D divided by Y naught plus J Y L 10 beta D, and this is, we substitute T here for 10 beta D and we substitute Y L equal to G L plus J B L, and then we can write Y in of this form Y naught G L plus J B L plus Y naught T divided by Y naught minus B L T plus J G L T. So, what we can do? We can now write Z in is equal to R plus J X is equal to 1 by Y in, and then from there we can find out the real part R to be equal to G L into 1 plus T square divided by G L square plus B L plus Y naught T whole square, and the expression for X also can be obtained, and it is given by G L square T minus Y minus T B L into B L plus T Y naught divided by Y naught into G L square plus B L plus Y naught T whole square. Now, we have R and X expression for R and X. We know that for our matching, this R has to be equal to Z naught, and once we equate R to Z naught, G L and B L, Y naught, these are being known, we can find out the solution for T. So, from the expression of R L, we can write, if we write R equal to Z naught is equal to 1 by Y naught, if we make this substitution, then we can, and then rearrange the terms, we can write Y naught G L minus Y naught T square minus 2 B L Y naught T plus G L Y naught minus G L square minus B L square equal to 0. Now, this is a quadratic equation, and this equation can be solved to get expressions for T. One particular case is when G L equal to Y naught. In this case, this term becomes 0, and here also G L Y naught. So, this G L square cancels, and we get a simple solution for T, which is minus B L divided by 2 Y naught. So, this is a specific case when G L equal to Y naught. If G L is not equal to Y naught, then we can solve t to be equal to the standard solution for a quadratic equation, we can write, and we can write t in this form. So, once t is known, we remember that t is equal to tan beta d. Now, we can get solution for d. So, we get two solutions for d, and d by lambda can be written as 1 by 2 pi tan inverse t when t is greater than 0, and this is 1 by 2 pi into pi plus tan inverse t when t is less than 0. So, we have two possible values of t, and depending upon whether it is greater than 0 or less than 0, we will get two solutions for d or d by lambda. So, with the values of t calculated, we calculate the value of x, and once we calculate, we have already shown the expression for x, and when we calculate the value of x, the necessary Stub reactance xs is equal to minus x. Now, as we have already said, the Stub can be realized either as an open circuited stub, or it can be realized as a short circuited stub. So, let us denote LO as the length of the open circuit stub, and LS denotes the length of the short circuited stub. So, we can find out Ls by lambda is equal to 1 by 2 pi tan inverse xs by z, and we know that xs is equal to minus x. So, once we substitute minus x here, we get minus 1 by 2 pi tan inverse x by z naught. Similarly, for the open circuit case, we get L open or LO by lambda is equal to minus 1 by 2 pi tan inverse z naught by xs, and this is equal to 1 by 2 pi tan inverse z naught by x. We are calculating the lengths of the stub. So, it may be noted that if any of the lengths come out to be negative, we can add lambda by 2 to get the actual stub length. So, let us now consider an example, and in this example we consider a load impedance ZL to be equal to 100 plus j 50 ohm, and this load impedance ZL is to be matched to a 50 ohm line. Then if we apply the analytical solutions, we get two values of t which are minus 0.333, which we call T1, and t is equal to 1, which we call T2. Now, corresponding to these two values of t, we also get two solutions for d, and d1 by lambda can be found out to be 0.045, and d2 by lambda can be found out to be 0.0125. Now, once we substitute these values of t, we get two solutions for x, and we call them x 1 is equal to 50, x 2 is equal to minus 50. And when we have two values of x, we can have also two values of the open circuited. Here we are using open circuit stub to do the matching. So, we can calculate the values for the length of open circuited stubs, and we call it LO1 by lambda is equal to 1 by 2 pi tan inverse Z naught by x 1, and this x 1 is 50. So, it becomes tan inverse 1, and therefore, it is pi by 4. So, essentially L 1 by lambda becomes 0.125, and L 2 by lambda, this is 0.5 plus 1 by 2 pi tan inverse Z naught by x 2, x 2 is minus 50. So, it becomes 0.5 minus 0.125, which is 0.375. So, we have found out the locations of the stub, where the stub need to be placed from the load, d 1 and d 2 in terms of lambda, and the corresponding values of the lengths of the stub, again in terms of lambda we have calculated. So, one stub is 0.125 lambda and the other stub is 0.375 lambda, and the matching can be obtained by placing these stubs at the locations what we have calculated. So, let us now move on to how we can do this matching, L section matching using a Smith chart. In the Smith chart, we first locate the point normalized impedance 2 plus j 1, and then we pass a line from the center of the Smith chart through this point. Also, we draw the constant VSWR circle, and we find that as we move from the load over this VSWR circle towards the generator, for the first time we intersect R equal to 1 circle at this point, and we pass a line through this point. Now, the wavelength value here can be read out. Similarly, the wavelength value here can be read out, and the difference of these two will give us the distance d, one of the solutions by which we should move from the load to place the stub. And at this point we find that the input impedance is 1 minus j 1. So, in order to do the matching for this point, we need to add 1 plus j 1. If we continue our journey this way, we find that we intersect the R equal to 1 circle once again at this point, which is given by 1 plus j 1. We draw another line. So, now we will have to move from this point over this circle, and this will give us another solution for the distance d, and here the normalized impedance is 1 plus j 1. So, the stub must provide a reactance of minus 1. So, we can find out the length. We know that this is the open circuit point, and starting from here, if we move across the periphery of the Smith chart, at this point we find plus 1 j corresponding to this solution, and this gives us the length L 1. And similarly, from this open circuit point, if we move towards the generator, this is the point where we get minus 1 reactance, and this is the length L 2. Now, this lengths L 1 and L 2 can be seen to be 0.125 lambda, and this one will be 0.375 lambda. And therefore, we now calculate the values of D in terms of lambda for solution 1. So, at this point we have the value 0.213, and at this point we have 0.338. So, the difference of these two gives us 0.125 as the length of the transmission line D, and after traversing this 0.125 lambda, we reach this point where we need to apply excess is equal to 1, for which L open by lambda is 0.375. The second solution, we have D by lambda is, this is 0.5 minus this distance, that means 0.213 minus 0.164, this arc length, and this comes out to be D by lambda equal to 0.451, and for this solution we require excess to be equal to minus 1. That means the length of the stub in terms of lambda is given by 0.125, where we get minus 1 excess as we travel down the Smith chart from the open circuit point. So, this completes our solution. We have found out the lengths of the stub, we have found out the location of the stub, and from our analytical calculation we find that these values agree with the Smith chart calculated values.